Okay, as always, you should attempt to do this problem first before you watch the video. Alright, I've got two different motions here. Let me make a drawing. So, part one of the motion goes 35 degrees down angle. Right, it's 35 degrees below the horizontal on a 2.1 meter long ramp. And the travel time is 4 seconds, and then it leaves the ramp and is in the air, falls down through the air for 4 seconds. No, for 1.5 seconds before hitting the ground somewhere over here. So the motion of the object when it's going down the ramp, I guess it's going like this. And then when it leaves the ramp, it goes into some kind of parabolic motion, like this. And when it hits the ground, it's kind of going like this, making, not going straight down, but it's making some kind of angle theta with the horizontal. And it lands some distance delta x away and travels some vertical distance delta y. We just want to know the magnitude and direction of the final velocity the instant before it hits the ground. Okay, so there are two different accelerations here. Right, remember that our equations of motion for constant acceleration only work during time intervals in which the acceleration is constant. So I need to split this up into two time intervals. There's an interval on the ramp and then the interval in free fall. Now on the ramp, we could split this up into x and y components, but there's really no need to do that. Instead, I'm just going to measure my motion along the ramp, and in that sense, delta s is 2.1. It starts at rest, has some unknown final velocity, unknown acceleration, and the travel time is 4.0 seconds. Well, from that, I can get the final velocity. That's all I really need. I just need the final velocity for part 1. That'll be the initial velocity for part 2. Okay, so to find that, I'll use the equation that doesn't have acceleration in it. That is delta s is 1/2 v plus v naught t. So v naught is 0. So that gives me that the final velocity is, I guess, 1.05 meters per second. Alright. So, just to comment on this, that's a pretty slow speed. But, you know, what that means is that the ball didn't just slide freely down the ramp. It didn't just slide down a frictionless ramp. There was obviously some friction or something like that, because that's only going 1.05 meters per second after 4 seconds. That's a very slow acceleration. But, okay, that's what we've got. So now this just becomes a free fall problem, which I hope will be pretty easy. For this problem, we need to split it up into x and y components and figure out what our different quantities are. So if you haven't already done this, you should pause the video and fill out this table, assuming we have our sign conventions that we'll generally want to make the direction of motion positive. So in this case, I'm going to make to the right positive, I'm going to make down positive. Okay? That'll be my sign convention for this problem. So with those sign conventions, I want you to do the best you can to fill out this table with the initial information given. Okay, so I'll start filling this out. I don't know delta x. V naught x, well, again, the final velocity for part 2 is the initial velocity for part 1, so v naught x is 1.05 cosine 35. Right? You have to understand that what's happening right now is that this ball is going into some kind of free fall right after it leaves the ramp, but that initial velocity vector is 35 degrees below the horizontal. And it has an x component, and it has a y component. Right? So V naught x is equal to V naught cosine 35, 1.05 cosine 35, that's 0.860. The x acceleration is 0, of course, since it's in free fall, so that means the final x velocity is also 0.860, and we're told that the travel time is 1.5 seconds. In the y direction, I don't know delta y. V naught y is 1.05 sine 35, and it is positive. Note that down is positive in this problem, so that's 0.602. Don't know the final y velocity. The acceleration in this case is positive 9.8 because down is positive, and the time is 1.5. So all I really need to do now is I just need to find the final y velocity, and then I'll have the components of the final velocity vector. So to find the final y velocity, I'll use the equation that doesn't have delta y in it. That's Vy equals V naught y plus AT. So that's 0.602 plus AT. That's 15.3 meters per second. Okay, so my final velocity triangle looks like this. If I draw a coordinate system, x and y, I have a little bitty x component, which is 0.860, and I have a really big y component, which is 15.3, and I need to find this hypotenuse here, which is the final velocity v. The final velocity v is found with the Pythagorean theorem. So 0.86 squared plus 15.3 squared. If I round this to 2 sig figs, it's really just 15 meters per second. And then the angle theta here, well, I know tangent theta is equal to opposite over adjacent, and therefore theta is the inverse tangent of opposite over adjacent, and in this case the side opposite the angle is 15.3, the side of the triangle adjacent to the angle is 0.86, that's 87 degrees below plus x. There's my answer.